Okay, so in today's lecture, we are going to have a look at few topics from Unit 1, that is image sensing and acquisition, image digitization, where we will be studying image sampling and quantization, and we are going to study about resolutions for images. Then we are also going to have a look at important statistical properties of images like histogram, profile, mean, and standard deviation. Okay, so a this is simple equation in which we can represent an image, or we can call this as image formation model. So your image fxy is given as illumination component into reflectance component. So ixy is illumination, or it is amount of energy uh, which is incident on the object, or which is incident on the scene. So ixy is nothing but illumination at point xy, and rxy is reflectance or transmittivity at the point xy. So this is amount of illumination or amount of energy reflected from the object. So any image point fxy is represented as product of the two components, illumination and reflectance. Now, according to your image capturing technique, this illumination component varies. Okay, so this reflectance value, these are the typical values for reflectance for these various objects. Or so for black velvet, reflectance value is 0.01. That's why we observe it as black, because there is very less energy reflected from the black velvet surface, and as very less amount of energy is reflected, that object is not visible to human eye. So for black velvet, reflectance value is 0.01. For stainless steel, it is 0.65. Then if you go for silver plated metal, it is 0.9. And for snow, it is 0.93. So as you move from black to pure white color, reflectance increases, because and as reflectance increases, it means it reflects almost entire energy which is incident on the object, and that's why we can observe that object as white. Okay, so these are typical reflectance values, and this illumination or energy incident on the object, it can take any value between 0 to infinity, and small percentage of this original energy is reflected. That's why this reflectance value is always between 0 to 1. And when this reflectance is multiplied by illumination component, we get actual value of the particular pixel at location x1. Okay, so this reflectance value is always between 0 to 1. So images are typically generated by illuminating a scene and absorbing the energy reflected by the objects in the scene. So as shown here, this is illumination source or energy source. This source is illuminating this particular object, and this object is reflecting energy according to its reflectance coefficient, and this reflected energy is captured by your image capturing device, and according to that captured value, it reproduces two-dimensional projection of real object, uh, and it assigns particular intensity values depending on R component, reflection component, and illumination component. These intensity values are decided. Okay, so this now source of illumination, it varies from application to application, or it varies from image capturing, from one image capturing technique to other image capturing technique. If we are considering standard digital camera for capturing the images, illumination source can be natural light, or it can be a flashlight which is generated from your camera. Now, if we are talking about medical applications, there are various types of modalities, and according to that modality, this illumination source or energy source varies. For X-rays, sources, X-rays. For ultrasound images, ultrasonic waves are used as illumination source or energy source. For electron microscopic images, this source is different. Okay, so according to your actual image capturing technique, this illumination source or energy source varies. Now, in your digital cameras, there are imaging sensors used to capture the image. So, incoming energy lands on a sensor material responsive to that type of energy, and this generates a voltage. Okay, so this is an example of single sensor which is based on charge coupled devices, and this sensor is illuminated by light energy, or it is illuminated by photons, and input photon energy is converted to equivalent voltage. It is stored in the sensor in terms of charge, and that charge is converted to equivalent voltage output. Okay, so this is an example of single sensor. Okay, but when we want to capture image of entire object, this single sensor is not very useful. So usually we have these sensors in terms of collection of sensors. So as shown here, we can have an array of image sensors which can capture the image of the given object in a single scan. Or we can also have line of image sensors, and these are known as strip sensors. Instead of a two-dimensional array, we can have a single strip sensor where multiple sensors are arranged on a strip as shown here. Now, if you have this strip of sensors, you need some image acquisition technique as shown here. If you have single imaging line as sensor or a strip sensor, in order to capture this entire imaging area, it is necessary to move this strip over the entire area. This strip has to be scrolled over entire imaging area. So you need linear motion of this strip so that entire image is covered. So this strip will give you output line by line. And in one line, you can have multiple sensors. So initially, you might have been positioned this line at this end, extreme left end. And so you will get first row of the image. Then when you move this strip by one row, you can get the second row. And similarly, by moving this strip over entire image, you can collect information of all the lines present in the image. Okay, so this is a strip sensor which you can use to acquire the entire image. But of course, here, as the information is collected line by line, you need greater time to acquire the entire image. So instead of that, you can use these sensors which are arranged in matrix form. Okay, So this is an example of array sensor, and in one scan, it gives you entire object image. Now, this is another type of sensor which is used in computer tomography. So here there is a ring, and on this ring, on one side, there is X-ray source, and on exactly opposite side of X-ray source, there are X-ray sensors. Okay, so this is your object for which images are to be captured, and this X-rays are uh, passed through this object and they are collected on other side. Okay, so this sense energy is collected by the sensors which are available on the opposite side of the X-ray source. Okay, so when now in order to capture one cross section of this object, it is necessary to rotate this ring uh, around this object so that it can capture cross sectional data of this object in 360 degrees. Okay, in order to get one cross section, it is necessary to rotate this ring uh, through 360 degrees. One rotation of the ring is required so that entire data can be captured. So with one rotation of the string, you can capture one cross section of the image. Now, with the same arrangement in computer tomography, you can get 3D picture of the object. So this 3D picture is constructed by using 2D scans of the object. And to get multiple 2D scans, what we need is we need to move this object linearly along this horizontal axis. So say in first scan, you are capturing cross section at this end of the object. Now, if you move this object inside, then you can get next cross section. If you move it inside further, you get third cross section, fourth cross section, and so on. And similarly, you can capture all the cross sections of this object. And in the end, by using some image reconstruction technique, you can reconstruct the 3D picture of your actual object. Okay, by collecting all these cross sections frame by frame, we can get 3D picture of actual 3D object. Okay, so this is brief conceptual introduction to computer tomography. So there are various capturing tools, and for every image capturing tool, its principle of operation is different. If you talk about magnetic resonance imaging, principle used is different. Okay, so that uses alignment of hydrogen ions or hydrogen ions in the tissue, and accordingly your body is magnetized, and alignment of those molecules gives you actual picture. So from modality to modality, or from one technique to other technique, you have different energy source and totally different mechanism for capturing the images. So this is an example of charge coupled device array type sensor. This is by Kodak, okay, which has pixel resolution of 2184 by 1472. So it basically converts your photon energy into electric charges. These charges accumulated in each sensor unit, and there is array of such sensor units as shown here. Okay, and finally output is available as voltage, and there is also analog to digital converter circuit, which finally gives you digital equivalent of each pixel intensity value. Okay, so this is an example of image sensor by Kodak, which is of CCD type, charge coupled device type. Okay, so now let us have a look at what is meaning of image sampling and quantization. So a digital sensor can only measure a limited number of samples at a discrete set of energy levels. If you look here, uh, there is an arrangement of sensors. So this signal captured from sensors is not continuous in nature, but it is available as discrete data. And placement of these sensors and size of sensors decide your spatial resolution of the image. So how the signal is sampled, it depends on actual sensor placement, and its size. Okay, so this spatial resolution is a term related to image sampling. Then there is another type of digitization or discretization, that is quantization. Quantization term all of you are familiar with. So this quantization is the process of converting a continuous analog signal into a digital representation of this signal. Okay, so this sampling deals with uh, discretization of x-axis and y-axis. Okay, so distance between samples along x and y axis, it decides spatial resolution of the image, and actual quantization or digitization of amplitude levels, that decides how many intensity levels are there in your image. So here you can observe a continuous signal. This line A to B is shown here. This axis is your x-axis, and this vertical axis represents amplitude of pixels from this particular line A to B. Here, instead of complete image, in order to understand concept of sampling and quantization, only one line of this image is shown here. Okay. Now, when we sample the signal, basically we digitize the x-axis. Okay, so we consider, as shown here, we consider discrete samples from this x-axis. Okay, so these small dots, they indicate samples according to your x-axis discretization. Okay, so there are various samples. So your x-axis is not continuous in nature, but we are only considering samples at these particular distances. They are placed at some unit distance. So we are not considering continuous axis, but we are considering these small sampling instances, and hence we are considering only these samples which are shown here by small circles. Okay, so this is meaning of sampling. And like this sampling of x-axis, we can also have sampling of y-axis by discretization along this vertical axis of this particular image. Okay, so if we consider entire image, we can have a sampling grid instead of these single samples, say sampling instances on x-axis. If we consider x as well as y direction, there will be a sampling grid. Okay, so this is about sampling. And now, instead of continuous amplitude signal, if we consider, if we quantize this amplitude axis, we get quantized signal. If we discretize this vertical axis, we get quantized signal. If after sampling, if you observe these sampled values, their amplitude is still continuous in nature. Okay, so when we when we discretize this amplitude axis, we get quantized signal. So instead of considering all amplitude levels, now we are simply considering, say, as shown here, 8 amplitude levels: 1, 2, 3, 4, 5, 6, 7, 8. We are considering only 8 amplitude levels, which are equivalent to 8 gray shades. Okay, so here, according to these 8 gray shades, we are observing here different discrete amplitude values, and this is nothing but quantization. Okay, so in chat box there is question: what is need to discretize image? So basically, uh, in order to, when we discretize image, basically we get digital data. After discretization, it is possible to represent it in digital format, and once we represent it in digital format, then only we can apply various algorithms on that image. So the main intention in converting your analog signal into digital signal, or converting it to discrete signal, main intention is making next processing of images very simple. It also gives you all other advantages of analog to digital conversion. Once we can represent it in digital format, we can take advantage of digital transmission, digital storage. Okay, and all of you know that digital transmission is more immune to noise. Okay, so all these advantages are possible only after discretization of the image. Okay, so this is main intention. Second intention is by using less number of quantization levels and less number of samples, we can represent same data in compressed format. Okay, we can apply various digital compression techniques on the image, and hence we can achieve greater amount of compression. Okay, getting this, Sharon? What is need of discretization or digitization? Is it clear? Okay, good. So let us move to next slide. Okay, so this is your original image, and in this picture only one line is shown in order to understand sampling concept. So for this one line we have only x coordinate, and this x coordinate is not continuous in nature, but it is a sampled version of x-axis. And after quantization, this amplitude of image or gray levels of image, those are quantized, and because of discretization, we can represent them in less by using digital techniques. We can represent them in terms of bits. Okay, so this is your uh, sampled and quantized signal. Okay, here we are considering only one dimensional data, that is one line of the image from the given image. So like this x-axis sampling, we can also have sampling on the y-axis, and in that case we can call this sampling as we can represent the sampling in terms of grid. Okay, so here this is digitizing the x coordinate and y coordinate values means sampling, and digitizing the amplitude values means quantization. Okay, so this is your continuous image. So when we sample it, we digitize the x coordinate. So as shown here, we are discretizing, or we are digitizing the x coordinate, which is as shown here, and we are not considering continuous signal, but we are considering sample values, which are represented by the sky blue lines. Okay. So here we are considering only these instances and we are considering these samples. Okay. So so this is your sampling grid. Now when we switch from one dimensional signal to two-dimensional signal, your digitized axis, coordinate axis, it now becomes a grid. Okay. So we are considering uh, digitized x coordinate as well as digitized y coordinate, and this output, this second image represents sampled as well as quantized image. If you look at the original image, at the center there is bright shade, and on borders or outer boundaries of the object there are dark shades. As you move from center towards outer side, this gray value is becoming darker and darker. And in this image, you can observe there are many gray shades between white and black. But if you look at this quantized picture, there are only 8 gray shades. As you move from center to outer border, number of gray shades are now reduced because of quantization. Okay. So here we are considering only 8 gray shades as shown here. These 8 gray values equivalent to these amplitudes, these gray values are considered. Okay. So you can observe here less number of gray shades as compared to this particular image or original image. Okay. So here number of gray shades are only 8. This is effect of quantization. Because of quantization, we are considering only these 8 values. And here this square nature or blocky nature is because of sampling operation. We are not considering continuous values, but we are considering samples from this grid. Okay. So because of these uh, sampling of x coordinate and y coordinate, here we are observing this image as boxes. It has some blocky nature because of sampling. But in here, in order to understand concept of sampling and quantization, large number of box size is used. Okay, but when we go for actual digital images which are captured by various digital techniques, here samplings, there are comparatively large number of samples and we are unable to observe this blocky nature. It gives you effect as continuous signal. It gives visually it looks as continuous picture. So your original image, though I'm saying this, I'm calling this as continuous signal, it is actually represented here using digital techniques. It is actually a digital image which is discrete in nature. It is sampled and quantized version of real continuous image. But because there are large number of samples and large number of intensity levels, here we are getting uh, say it is we are getting effect as this is continuous image. Okay. So this is your digital image. So say if you have this as image where a character D is written. Now in this image, this is your X coordinate, this is Y coordinate, and this is origin. Okay. So this XY coordinate plane, it gives you image space or image plane. Okay. And now for this particular image, there are 3 gray levels, right? Or 3 intensity values. Your D letter is written in white color. This border is black and background is gray. So these 3 levels in continuous sense, they can be represented by value 0, value 1 and value zero point 0.5. If we consider this as continuous signal between 0 to 1, we can say value for black color is 0. For white, it is represented by 1 and gray is represented by zero point 0.5. Now, instead of continuous signal, if we assume that there are 8 bits per pixel, in that case, your white color is represented by which value? If I say there are 8 bits per pixel, then what is value for white color? Please type in the chat box. If I'm using 8 bits per pixel, okay, just tell me what is, yes, Sharon, if I'm using 8 bits per pixel, white will be represented by 255, black will be represented by 0, and this gray will be represented by level 128. Okay, so this is representation of digital image. And now if you plot this uh, gray value as third axis, fxy amplitude, your same image will be represented as shown here with 3D representation. This is your x coordinate, this is y coordinate, and fxy represents actual amplitude values. So wherever d is written, you have maximum amplitude. Wherever there is black border, you have minimum amplitude, and wherever there is background which takes say value 120 in digital format, okay, so this is represented by this particular box. Okay, so that represents background. So these are various representations of the same thing. When we visualize it as image, it will look like this. If we plot gray value as third axis, amplitude axis, it will look like this. And when we store it in storage medium, it will take values as shown here. Okay, so these are various representations of the same thing, same image. Okay, now let us talk something about spatial resolution and gray level resolution. So the spatial resolution of an image is determined by how sampling was carried out. Greater the number of samples, greater the spatial resolution. Lesser the number of samples, lesser the spatial resolution. So spatial resolution simply refers to the smallest discernible detail in an image, smallest measurable change, or smallest noticeable detail in an image is nothing but spatial resolution of the image. And it depends on how the image is sampled. Okay, so here this is an example of an image where 1024 by 1024 samples are used. So your sampling grid size, this sampling grid size is 1024 by 1024. Now, instead of that, if we use less number of samples, okay, so if we consider half of this resolution, there will be 512 by 512 samples. If we further reduce it, you can have 256 by 256 resolution, and so on. You can have say 32 by 32 samples. Okay, so by as we go on reducing the number of samples over given distance, spatial resolution goes on reducing. Okay, so let us talk it in terms of matrix. Okay, so instead of this image, this has very big size 1024 pixels by 1024 pixels. Instead of that, say if we have 8 by 8 image as shown here. Okay, so this 8 by 8 image is represented here as two-dimensional matrix with 8 rows and 8 columns. Now, if we reduce resolution by half for the same image. Okay, here some numbers are written. If we reduce its resolution by half, what will happen? In that case, instead of 8 by 8 samples, we will have simply 4 by 4 samples, because when we reduce resolution, we are considering, as compared to this image, we are considering alternate samples, because we are reducing number of samples over given distance. Here initially there were 8 samples along x-axis, there were 8 samples along y-axis. Now if we halve the resolution, there will be only 4 samples along x and 4 samples along y. So effectively, we get only these sample values, right? So when we reduce number of samples, instead of all these 8 by 8 samples, now we have only 4 by 4 samples, right? So we will have only 10, 12, 14, 10, and so on in all these rows. So similarly, we have 4 rows. If we reduce it further, what will happen? Say if we uh, further reduce resolution by half, what is the resultant image size? If we reduce the resolution by half as compared to this image, yes, we will get 2 by 2 image. So we take these alternate samples 10, 14, 10, 14, and we will get only 2 by 2 image, because over this actual image distance, now instead of considering 8 samples, now we are considering only 2 samples. So we will get an image of size 2 by 2. Okay. Now, if we want to represent original size image simply by using these 4 samples, what we need to do? We need to uh, upsample the image, right? Or in for digital images, we can call it as zooming operation. So from this 2 by 2, from this low resolution image, if I want to reconstruct image of original size, what I need to do is I need upsampling of this data. How I can achieve it? I can replicate same sample over remaining samples. Okay, I can replicate this same 10 here, 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 and till this location. I can replicate 14, total 16 times. I can replicate value of 10 over these 16 locations, and I can replicate this value over all these locations, so that I can, though the resolution is less, if I want to reproduce the image of original size, I need to upsample the data. I can represent the original image by upsampling as shown here. Okay, so we have replicated same sample 16 times over this square. 14 is replicated here, 10 is replicated here, and 14 is replicated here. Okay, so when we capture the image at low resolution, and if we have the same display device, and if we want to display the image with same size as original image, we need to use upsampling to represent the image. Okay, now this is your original image, okay, which
Ma'am,
is, uh,
ma'am, what is 11, 12, 13, 14? Are they value
these
of
are
K?
gray shades, gray levels, or
Okay,
amplitude values. Good that you have
okay.
asked this question. So if there is anyone else having the same doubt, these are pixel values or intensity levels. Okay, and because of low resolution capturing device, say we have only 4 samples as shown here, and but we by upsampling we can reconstruct the image of original size. Okay, so this is an image captured using say higher resolution technique or device, and this is same image captured using lower resolution device. Now can you recognize difference between these two images? Can anybody tell me something by comparing these two images? This is an image with resolution 8 by 8, and this is an image with resolution 2 by 2. So can you compare these two arrays?
Ma'am, the 8 by 8 will be more precise because it has more range of gray values.
Yes, correct. So you will get more precise result, or you can capture all the details. Intermediate details are captured because this is captured using greater resolution, and this image is captured using low resolution. So intermediate details are lost, and effectively this will look slightly blurred image. Okay, because same value is replicated over greater region. So visually, this will look as blurred image, or sometimes if resolution is very small, you can observe blocky nature to the image. Okay. So the same thing now, if you compare your different mobile cameras, one with higher resolution, one with lower resolution, you will observe that lower resolution image quality is uh, lesser than that of your higher resolution device. Okay. So similarly, you can say if your resolution is 4 by 4, you can reconstruct original size by replicating these samples. Now from 4 by 4, if you have to convert it to 8 by 8, compare here you need to replicate this number 10 at 4 locations. Okay. So as compared to 2 by 2 image, 4 by 4 resolution image is better in quality, but as compared to 8 by 8 resolution, it is of course less in quality. Okay. So the same thing is displayed here. This is original image captured with resolution 1024 by 1024. This image is captured by using resolution 512 by 512. And for all next images, resolution goes on decreasing. And this last image is captured using 32 by 32. And now if you compare this image with this image, you can easily observe here blocky nature or blurred nature because of low resolution capturing device. Okay, so now is the concept clear? What do you mean by spatial resolution and how the resolution affects image quality? Okay, the same exercise we did here in terms of numbers. Okay, numbers are representing intensity levels. Okay, so in terms of numbers you can easily understand how the details are lost because of low resolution. Okay, and here you can observe visually how the quality with higher resolution is better than the quality with lower resolution. Okay. So this is about spatial resolution. Now another term resolution with respect to images, that is intensity level resolution. So intensity level resolution refers to the number of intensity levels used to represent the image. The more intensity levels used, the finer the level of details discernible in an image. Intensity level resolution is usually given in terms of the number of bits used to store each intensity level. Okay, so if you use more number of bits, more number of intensity levels are available. If you use only one bit, it is binary image and it can have only two values, 0 and 1. And as you go on increasing the number of bits used to represent the image, more number of intensity levels are available as shown here. So if you have 8 bits, total 256 intensity levels are available ranging from 0 to 255. Okay, as shown here. So this is an example of images with different intensity level resolutions. So this is binary image where there are only two intensity levels. Here you have four gray levels. You can easily identify those four gray levels. There is one black level which represents boundary. Then there is white level. This is second level. Then there is dark gray as shown here near the outer boundary, and majority portion is shown by bright or light gray level. Okay, so there are only four gray levels, and as you move upwards, here this is an image with highest gray levels. Here there are 256 gray levels. Okay, so with more number of gray levels, more details are visible. So if you compare this image with this image, here you can observe more details. You can observe here details of the jaw, right? These are X-ray images. You can observe details uh, here in this section. Also, you can observe details in this particular portion because more number of gray levels are used here as compared to this image. So this is intensity level resolution. So there is one more example. So in this particular image, this is binary image, only two gray levels are used. And in this image, 16 gray levels are used. Okay. So is the difference between spatial resolution and gray level resolution? Is it clear to you all? Please type yes or no. Spatial resolution deals with sampling, how you are sampling the x coordinate and y coordinate, or what is size of your sampling grid, that decides spatial resolution of the image. And uh, gray level resolution deals with quantization levels. Okay, greater the number of quantization levels, greater the gray level resolution is. Okay, so is the difference clear to you all? I'm getting very few answers. Yes. What about others? What about others? Did you get the idea or concept of gray level resolution and spatial resolution? Very few answers are yes, either remaining they are not paying attention, or I'm unable to convince them difference between spatial resolution or gray level resolution. Okay, now I'm getting many answers. Good. Okay. So now always there is a uh, question with resolution. Uh, it's all how much resolution is enough. There is always this question. So this all depends on what is in the image and what you would like to do with it. So from application to application and from type to type of image, this how much resolution required is varies. So the main question or key question is, does the image look essentially pleasing? This is of course required. And second is, can you see what you need to see within the image? So it will be more clear with this example. Okay. So if you have an application of counting vehicles on a road, in that case, this resolution is sufficient. You can easily observe there are one, two, three, and four. Four vehicles are there. So you for this application, you may not need higher, you don't need higher resolution. If low resolution picture can suffice your purpose, why to go for higher resolution? Because with low resolution you need lower amount of storage. Okay, but if the application is recognizing the number plate, is this resolution sufficient? Of course not, because with this resolution, we are not at all able to see or read the number plate. So if the application is number plate recognition, in that case, of course, you need better resolution as shown here, where you can read the number plate easily. Okay. But if the application is counting the vehicles, in that case, lower resolution is sufficient. So answering this question is really difficult. It varies from application to application. It varies from what is your need. Okay. So then it also depends on image type. So this is example of low detail image. This is an example of medium detail image. And this is an example of high detail image. Okay. So here there are many people, they are making various hand movements, gestures. Okay. So there are lots of details in the image. So these are examples of image types according to the image contents, image details. Okay, so this is low detail image, this is medium detail, along with some foreground cameraman. Here a cameraman is standing with there is some background in the image, foreground in the image, but as compared to this, there are more details, and this is high detail image. So how many intensity levels are to be used? That also depends on details in an image. If you have large detail image, you can get the same quality image by less number of intensity levels. But for low detail images like these two example, you need greater number of intensity levels to get same quality image. Okay, so here these are the curves known as isopreference curves. So it represents the dependence. This graph actually represents the dependence between intensity and spatial resolution. On x-axis there is spatial resolution. Okay, n represents spatial resolution, and k represents how many intensity levels are there. Now, if you look at the curve for crowd image, that is this high detail image, you can observe that it is almost parallel to this vertical axis. And this curve represents images of same quality. Okay, so points lying on the curve represent images of equal quality as described by observers. Okay, so this here we are talking about simply about visual quality of the image by observers. So this for crowd image or for high detail image, this line is almost vertical. What it indicates that though you reduce the intensity levels, it gives you same quality of the image. So for the given resolution, spatial resolution n, we can select either 4 intensity levels or 5 intensity levels or more number of intensity levels. It gives you same quality. So for high detail images, we can go with less number of intensity levels, because though we increase number of intensity levels, it is not going to add to quality of the image. But it is not true for face and cameraman images. Or for low detail images, as you increase intensity levels, you get better and better quality. For the given size of the spatial resolution of the image. Okay, so I think it's 12:30. So that's all for today. We will start with statistical properties of images in the next lecture. Okay, so today before leaving, please type your roll number. Now, instead of roll number, I request all of you to type 5 digits of your PRN number. 5 digits of PRN number, space, and then your name. Okay, because it becomes easy for me to rearrange your numbers according to PRN numbers and enter in the ERP. That becomes easy. So I request all of you to type your attendance as your 5 digits of PRN number and followed by your name. Last 5 digits starting from 8. For example, 80965 Prakhar Sethi. Okay. Thank you all. If you have any queries, please ask. You can unmute and ask. Okay. Thank you all.